Hi, it's Terry Dennery of the MathWorks. So in this video, this is my first video for a new series I'd like to kick off, right? And in this series, I'd really like to introduce Simulink in a really good way and show how good it is for developing embedded controls, right? And so what our simple initial system is a DC motor driving a simple mechanical shaft. Mechanical shaft will be defined by its inertia as well as its damping constant, right? So why don't we just go ahead and hit run. Oops, that's the previous calculation. We'll kind of get there in a minute, right? But here's our initial trajectory, right? And so we've commanded a trajectory in this first block on the left. And we've essentially had to do something simple. We had to do one rotation. So you'll see its angle as measured in radians goes from 0 to 2 pi, right? And the whole transition takes place in 3 seconds, right? And I look and I know it's really good, okay? And maybe be able to explain that as we move through this even, right? And so anyways, what I want to do now is do a harder problem, all right? I want to go from 0 to 2 pi. Oops, let me show that. 0 to 2 pi in half a second, right? And so let's go ahead and run it from here. And now we'll see it doesn't do quite so good, right? And what's being revealed kind of very clearly now is that there were two curves and that we only saw one because the two matched very well, right? And that what we have here in yellow is what we want to happen, the command signal, and what we see here in blue is what we would get if we had a motor and mechanical shaft combination that represents what we have in this example. Okay, so the reason for this is really kind of simple. It's almost kind of obvious that the motor is not powerful enough to do what we want it to do, right? Now, power is one of those tricky terms because it's kind of a combination of torque as well as speed, and most motors really are defined for both. And we'll kind of get into where these terms come from and maybe what they really mean as we go through the series. But for right now, the speed's defined mostly through what we call the no load speed definition. And the torque um, is mostly defined by what we call the stall torque. Okay, so let's hit that, right? And now hit run. Okay, and it's perfect again, right? And just kind of a couple of simple concluding points. Is that again, I think we kind of got the fundamental pieces for almost any control system, at least for any control system for an electromechanical system, will be defined by its mechanics, by its actuation. In this example, it's a simple DC motor, and then its control. And the control can be really kind of separated into kind of the feedback, but as well as the feed forward. And feed forward, in my opinion, is pretty interesting. You'll see as I double click on this block, that I'm telling my feed forward controller what shaft inertia is and what the damping constant is. So I'm essentially informing my overall system through the feed forward controller of what the system itself is and why that's important. We'll hopefully kind of make the case for as we move through this. So anyways, hopefully I'm showing you some stuff that's of interest to you in this initial video, and I'd love it if you could, if you find that it's going to motivate your interest to watch the rest of these videos. I think they're going to be good. Thank you.